Hello, folks, and welcome. Welcome back. So, let's go ahead and at this point finish up chapter 21. But I will begin by reminding y'all how we got started. We basically understood in section 21.1 that there are two different types of charges, positive and negative. We also understood the notion of charge conservation and the quantization of charge. Then in section 21.2, we basically understood how charges can be or how objects can be charged by induction. In section 21.3, which is perhaps the heart of this chapter, we understood Coulomb's law and understood also that there are big analogies between Coulomb's law and the law of gravitation, Newton's law of gravity. Um, then we essentially went and embarked on two sections further, 21.4 and 21.5, which basically introduced us to the notion of the electric field. So notice that just like the Earth's gravitational field is ever present, even if there is nobody there to measure it, in an entirely analogous fashion, the electric field around a charge is always present, whether or not you have a test charge present to measure it. Now, of course, we understood also that using a unit positive test charge, a unit point-like positive test charge, you can actually measure the existence of the electric field at various locations. Once we did that, the lesson split up into two parts. One is how to find the electric field around a configuration of charges, and we specifically focused on the dipole and understood in detail how its electric field is obtained. And then we actually understood that for various devices in section 21.5, we might have an extended distribution of charges, and we actually went ahead and taught ourselves how to deal with an extended distribution of charges and how to find the associated electric field. So with that, we covered a lot of ground associated with the electric field. However, notice from the figure on the left that anytime you depict the electric field, you will basically be drawing many little arrows, and that is sometimes inconvenient or even tedious. So we want to know if there is perhaps a more pictorial, a more easy way to display the electric field. And in fact, we know from our study of magnets and bar magnets that in fact the things like magnetic field lines, which basically connect the north pole of the magnet to the south pole of the magnet. So we anticipate that there should be something like electric field lines that give us a more easy, a more accessible description of the electric field. So in the left panel, you see electric fields. And now let's go ahead and just connect the arrows together. So you connect the head of one arrow to the tail of the next arrow, and so on and so forth. And you can essentially draw a line like this. A line like this, for example, out here, and a line like this, for example, out here. And you can continue that process, essentially drawing lines like so. And you can then ask, what depiction did you get from this process? And the answer is that you will get a picture that looks very much like this out here, namely the picture on the right. So we understand that connecting the arrows together essentially gives us a representation of the electric field lines. So on the left panel, and I'll go ahead and erase the lines that we kind of put. In the left panel, you have an electric field being depicted. In the right panel, you have electric field lines being depicted, and we have a reason to think that the electric field line depiction is easier to display, and it conveys, hopefully, the same type of information. So we understand that in terms of communicating information, it might be beneficial to communicate such information with electric field lines. However, realize that we have to have some way of making the journey back if we so wish. So we start with electric field, we obtain electric field lines, but with the information about electric field lines, we have to have the ability to go ahead and retrieve the electric field at any given location. So notice that the electric field consists of a vector, and we want some strategy to take the picture in the right lower panel and retrieve from it some insight about the electric field itself. By scanning these two pictures, it's easy to see that the tangent line at any location on an electric field line actually gives us the electric field at that location. So that is easy to see. So we make the connection that the electric field vector is actually tangent to the electric field line at any point. So that gives us the direction of the electric field vector. But realize that a vector has magnitude and direction. So how do we retrieve the magnitude of the electric field vector when you have a depiction of the electric field lines? An interesting idea comes to mind that let's go ahead and put maybe a sheet of paper with unit area out here and ask how many electric field lines are crossing that sheet of paper out here at this location. And we see that indeed there are two electric field lines crossing it. If you take the same paper and hold it out here, you see that there's only one electric field line crossing it, and this gives us the intuitive understanding that the number of field lines crossing through a unit cross-sectional area gives us a good measure of the magnitude of the electric field. So we see that we can use the electric field line to basically retrieve the electric field vector, or the direction of the electric field vector. So starting with the electric field line, you can retrieve the direction of the electric field vector. So we obtain the direction, and we can also obtain the magnitude by basically saying that the number of field lines crossing through our unit area is proportional to the strength of the electric field itself in that location. So you see that the electric field is stronger closer to the positive charge and weaker farther away from the positive charge. So all of that begins to make sense. And now let's go ahead and proceed. So we understand from the lower two panels that we made a two-way connection. We can start with the electric field and obtain electric field lines. We can then start with the electric field lines and retrieve the information associated with the electric field. This picture actually makes the connection a little more visual and a little stronger. So we see that we have the same electric field lines crossing the littler sheet A and the bigger sheet B. So where do you think the electric field itself is stronger? The answer is that the electric field is just proportional to the number of electric field lines divided by the area. And we see that the same field lines cross the sheet A as they cross the sheet B. Therefore, you have a smaller area for sheet A than you have for sheet B. Therefore, the electric field at the location of sheet A is stronger than the electric field at the location of sheet B. So that's an interesting and important idea to reinforce. And it builds on the idea that we developed in the previous transparency. So let's go ahead and continue our studies. Now let's go ahead and ask what we obtained for the electric field lines associated with a positive charge, and the corresponding actual experimental visualization of those field lines is actually shown to you out here also. So we can actually go ahead and say that the electric field lines radiate outwards. And we also want to realize that the electric field associated with a stronger positive charge will in fact be stronger. So the only way to depict that is to say that the number of field lines coming out from a stronger positive charge will in fact be greater. So the larger the positive charge, the greater the number of field lines emanating from it. So with this insight, we actually go ahead and make a quantitative connection between the number of field lines and the strength of the charge itself. Now we've also studied that the electric field points into a negative charge, and that is again reinforced by the fact that the corresponding electric field lines go ahead and point into a negative charge. So electric field lines emanate out of a positive charge. As you saw in the previous figure, electric field lines radiate inward into a negative charge, as you see in this figure out here. Just like in the previous figure, we can actually say that the greater the negative point charge, the greater the number of field lines that are being directed into that charge. Okay? So field lines emanate out of positive charges. They go ahead and radially propagate into negative charges. And that's an insight that we've developed based on the pictorial notions that we've put forth. So this gives us some general guidelines or criterion for now going ahead and drawing electric field lines, because we see that electric field lines constitute a very useful visual depiction. So we realize that if you have a configuration of positive and negative charges, then electric field lines must begin on a positive charge and terminate on a negative charge. If you have a balanced situation where you have as many positive charges as you have negative charges, then all of the field lines beginning at a positive charge must go ahead and terminate on a negative charge. Now, in case you have an excess of one type of charge, then let's say you have 2 units of positive charge and only 1 unit of negative charge, then some of the field lines coming from the positive charge will actually indeed end at the negative charge, but the other field lines coming out of the positive charge will end at far infinity. So that's the idea that we will go ahead and talk about, and there'll be an example coming up in a couple of transparencies which emphasizes this for you. So let's go ahead and proceed. Now we understand that in order to retrieve the magnitude of the electric field, we have just to measure the number of field lines crossing a unit area. So we can actually go ahead and retrieve the magnitude of the electric field. And we can also retrieve the direction of the electric field by realizing that the direction of the electric field is always the direction of the electric field vector is always tangent to the electric field line. Now notice that at any location you should have a unique electric field. And because you have a unique electric field, you cannot, and because you realize that the electric field line is always tangent to the electric field, you realize that you cannot have a situation where two field lines can cross one another. And then, of course, let's go ahead and see the connection between the magnitude of the charge itself and the number of field lines associated with a charge. So we see that number of field lines leaving a positive charge or approaching a negative charge is indeed proportional to the magnitude of the charge itself. So field lines give us a very comprehensive picture of the electric field, and we will see how this picture becomes even more important when we get to the next chapter, where we develop the important idea or the important law associated with Mr. Gauss. It's called Gauss's law. So that's a very important topic of study, and field lines will essentially help make Gauss's law much more simple and accessible to us. So now let's go ahead and do a few more examples. So imagine, if you like, that you have an electric dipole. What's an electric dipole? We emphasized that in the last class itself. So if you have an equal positive and negative charge that are separated by a certain amount of distance, then that constitutes an electric dipole. And in the right panel, you basically see an electric dipole, and the electric field lines associated with that dipole are shown to you. Notice that since you have equal amounts of positive and negative charge, all the field lines that emanate out of the positive charge, in fact, terminate at the negative charge. You might say that this field line is emanating from the positive charge and it's not terminating anywhere, but if you allow it to go a sufficient distance, it will go ahead and turn around and come back to the negative charge. The panel on the left basically shows you how we visualize in practical terms these electric field lines. The panel on the right shows you an idealization. So we essentially see that the idealization and the actual practical experimental visualization of electric fields has kind of a good concordance one to the other. With that, let's go ahead and talk about a situation where you have two positive point charges. That again is shown to you schematically in the right panel and based on an experimental setup in the left panel. Unfortunately, the experimental setup doesn't produce a very crisp picture, but you can essentially see that now, since both charges are positive, they both have electric fields emanating electric field lines emanating from the positive charges. However, there are no negative charges in the system where they can terminate, and therefore all the field lines eventually have to rush off to far infinity. And that's actually giving you another interesting picture. So imagine, if you like, that you look at this configuration of two charges, but you look at it from very far away. Then it will seem to you almost like the two charges are practically fused to one another. And so you realize that far away, if you're looking at the charges from far, far away, the two charges essentially look like a single charge with a radially oriented electric field, just as you would have for a point charge. So this actually gives you a picture of why, or it gives you an understanding of why the electric field lines, seem to rush away to far infinity. So this guy is going off to infinity, 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 and so on and so forth. Okay? So far away, this configuration of two separated charges will look almost identical to a single charge with a charge of plus 2q. So with this, let's go ahead and do this practical example where I will actually urge you to realize that we have two unbalanced charges. So we have a charge of plus 2q, but we have a charge of only minus q to the right of it. So what will happen out here? You realize that there'll be twice as many electric field lines coming out of the charge of plus 2q as there are going into the charge of minus q. So you can actually do a real, literal counting up and realize that you have 1, 2, 3, 4, 5, 6, 7, 8, and you go ahead and double that because of symmetry. So you have 16 electric field lines coming out of this positive charge. How many field lines are going into the negative charge? If you have 16 field lines coming out of a charge of plus 2q, then into the charge of minus q, not minus 2q, but minus q, you should have only 8 field lines going into it. So this tells you that if you have a visual depiction of field lines, you can actually go ahead and make at least a relative or qualitative assessment of the amount of charge in that particular system. So that's a useful idea, and that idea is actually reinforced in this thought question where we're essentially asking you what is the ratio of the two charges that you see. Again, you can see that the electric field lines are coming out of one charge, which gives you the clue that it might possibly be a positive charge, and the electric fields are going into the other charge, which gives you the idea that it might be a negative charge. So we're just asking you to give us the absolute value of the ratio of the two charges, not necessarily the sign, but the absolute value of the ratio of the two charges. So think about that, and we might address this when we come to class also. So this gives us a lot of insights about electric field lines. Now it's time to move on to something else. So we understand, and we've essentially reminded you that the gravitational force, F sub g, can always be written as the mass m times the gravitational acceleration, which is a proxy for the gravitational field, we can similarly go ahead and write the electric force F sub E as being equal to the charge Q times the electric field itself at any given location. So we realize that there's a big analogy out here, but once you identify a force, you can actually identify the motion of a particle that responds to that force. And that is what we want to focus on in this section. We have already mentioned that there's a small bit of nuance when we go from gravitational forces to electric forces. For example, we mentioned that m will always be positive. So the gravitational force will always be parallel to g vector. On the other hand, the electric force can be parallel to E vector or it can be anti-parallel to E vector depending on the sign of Q. So if Q is positive, F vector and E vector will be parallel to each other. If Q is negative, F vector and E vector will be anti-parallel to each other. So please keep that little point of detail in mind because it can sometimes cause slip-ups when solving problems. So now, if you find the force, if you find the electric force, which is Q times E vector, then you realize that that force from Newton's second law should be equal to the mass times the acceleration vector. So we can therefore find the direction of the acceleration of a charge, and I will essentially underline this because this is exactly what we underscored even as we were discussing the previous transparency. So it causes trip-ups with some students on some problem-solving issues. So let's go ahead and emphasize this and make sure that you guys don't trip up. With that, let's go ahead and do an example of motion of charged particles in electric fields. And so we have this situation where an electron, which is negatively charged, comes zipping in horizontally in this region where you have a pair of charge plates. So you have negative charge plate and you have positive charge plate. And in the next chapter, you will see that if you have this configuration of two charge plates parallel to each other with opposite signs of charge, then you will actually set up an electric field. And you will see in the next chapter that the electric field goes from the positive charge plate towards the negative charge plate, and the electric field is in fact uniform. So you have a uniform electric field, and that immediately reminds you of the Earth's gravitational field. The Earth's gravitational field, at least measured on short distances, is also uniform. And we then go ahead and ask, what is the force on this electron that goes into this um, region where you have a non-zero electric field? And the answer is that that force is just equal to Q times E, or it's equal to the charge of the electron times the electric field. But notice that the electron is negatively charged, so that even though the electric field points upward, the electron, in fact, feels a downward acceleration from this charge. So we'll go ahead and solve this problem. And as with any problem involving Newton's second law and finding the motion of a particle, we will go ahead and begin by saying that we have the charge of the electron times the electric field, and this is acting downward, which is equal to the mass times the acceleration in the y direction in this figure. So that immediately gives us the acceleration in the y direction, and we obtain ay is equal to minus little e times big E divided by m. Little e out here stands for the charge of the electron, 1.6 times 10 raised to minus 19 coulombs, and big E stands for, in fact, the electric field. The mass m is the mass of the electron. So once we've obtained the acceleration, we realize that there is no acceleration in the x direction, but there is an acceleration in the y direction, and therefore we can essentially solve the equations of two-dimensional motion. So we can actually say that if we're dealing with x-directional motion, the final position xf is equal to the initial position xi plus vx times t, and the x velocity does not change because there is no acceleration in the x direction. So we can go ahead and take our initial position as xi and yi, or alternatively, we can essentially reset our origin to be at this location, which is the simplification that has been taken place, that has been used in this picture. With this, we can essentially go ahead and ask, what is the y directional motion? And we go ahead and say that y final is equal to y initial plus vy times t plus half of ay times t squared. This is just an expression of a kinematic law. However, notice that vy, the initial y velocity, is 0. So we can discard that. And we also realize that ay is in fact negative and has to be obtained from this equation. So we can now go ahead and simplify our equations. So we will obtain yf, and we'll take yi to the left. So we have yf minus yi is equal to, for vy we have 0, and for ay we know it's negative, so we obtain minus little e times big E divided by 2m out here times t squared. Now, how do we fulfill t squared? Because notice that what we want to do is essentially obtain an equation for the trajectory of the electron. We can actually go ahead and use our intuition to realize that if the electron is undergoing uniform acceleration in the minus y direction, that is very similar to some situation that we've seen in physics 1, namely if you go ahead and send a projectile horizontally in the Earth's gravitational field, that projectile will essentially follow a parabolic trajectory as it sinks downward to the ground. So we know that we might have an entirely analogous situation out here, but we have to eliminate time in this equation that we have just written. And the way to do that is to basically use the other equation. So we can write t as being equal to xf minus xi divided by vx. And we can go ahead and substitute this expression for the time into this equation out here. So let's go ahead and do that. We have yf minus yi is equal to minus little e times big E divided by 2m, where m is the mass of the electron and little e is the charge of the electron and big E is the electric field. And in place of time, we use this expression out here, and so we have xf minus xi divided by vx, the whole thing squared. Okay, so we've just gone ahead and replaced the time with this expression, and now we can go ahead and simplify. In fact, I can simplify it even further by taking xi and yi to be just equal to 0 and 0. In other words, we choose our origin to be the starting point of the electron's motion, and therefore we obtain yf is equal to minus E times big E divided by 2m times Vx squared in the denominator times xf squared. So we see that we have essentially the equation for a parabola exactly as we anticipated before. So we have a parabola going down, and that's what we have out here. Okay, so with that, we've basically gotten a good understanding of how particles move in electric fields. We usually use simple configurations for electric fields to just make it easy for students to understand this. And so with this, I will go ahead and thank you all. And we've completed this chapter, and hopefully, okay, so we have nothing on the next transparency. And we've completed this chapter, and I look forward to seeing you all in the next chapter. I hope you found these lectures useful and use them to reinforce your learning and make sure that you understand the subject with some mastery. So with that, thank you and see you again.